Okay, so we've got a good picture here for a larger graph. We have about 12 nodes, and we're going to be taking a look at this as well next week. So I'd like you to become more familiar with this specific graph. It's not like you need to memorize it or anything, but just having seen it a couple times will help. The data I've got printing out, just to double check for the locations, because we've got the XY plane, you can think of the x-axis as increasing as we move to the right. And then just a reminder that with your Java Swing and Auth library, you have the y-axis increasing as you go down. And if we take a look at the data that I put in a couple of int arrays, we've got the points and the lines that I would like to draw. Now I take a little bit of inspiration from working with graphics, and you've got OpenGL, and you've also got other frameworks just for working with a graphics pipeline and a GPU. Part of the issue with describing geometry is you would want to draw triangles, maybe something like this. I mean, I'm not thinking in 3D here, but if you look at the graph with 0, 1, and 2, it goes in counterclockwise order when you look at that triangle. And that tends to be the way that you describe the geometry for a 3D triangular face. And if it goes in counterclockwise order like that, then you can imagine that this would have a solid filled color inside the triangle facing towards your viewpoint. And if you rotated it in 3 dimensions so that it would have the vertices and the nodes 0, 1, 2. If it went the other way, 0, 1, 2 clockwise order, then you wouldn't see the filled in color. It's a way of describing whether you have a triangle facing towards you or away from you. And you can also have geometry where there's 2 sides, and you could also show both sides if you really want. Now I'm taking inspiration from the way they lay down the indices, and they've got a bunch of arrays that you need to fill in all the data with. So very similar here. We've got the points where we would like to describe each node. So node 0, I've described first. We have it in location x, 30, y, 300. So I go in from the left a little bit by 30 units, and then 300, I would come up from the top and go down to 300. So you know my window size is about 800 by 600, and 300 is right in the middle. Okay, if you look at the next node, we've got node 1, 150 by 500. So just to give you a little bit of better idea how we've decided to lay things out in the window, I go in by 150 units, and then I would go down by 500. And then node 2, we've got same horizontal number of units, and then only down 100 units. So you could read off the other coordinate pairs, and you could see how each pairs of values in my array I'm using to decide where to lay down each node. And I'm doing it in the order that you see appearing in the points array, and we've got each node numbered in that order. So we've got all the way from 0 up to 11, there's 12 nodes. And then when you think about describing the locations for the lines between the nodes, you have to describe the starting point and the ending point. And you don't have to repeat the descriptions for all this information. You've already got the nodes, and you know that the starting point and the ending point is going to be at where the nodes are. So what you can get away with then, instead of these larger numbers, is you can describe the edges again in pairs, but instead it's the labels for the nodes that I can give. So this first edge from 0 to 1, I can just list off that way, 0, 1. And so I'm filling up this array to describe all the edges, and each pair describes one edge. So I'm listing pairs of nodes by labels. Now, you could decide in 3D geometries to do something similar. You describe the vertices, which is what they call them instead of nodes. And then similarly, when you're describing the triangles, you'd give 3 vertices and you'd go in counterclockwise order so that it could know whether a triangle is facing toward the camera or away from the camera. So same kind of idea, but we don't have to worry about ordering. I don't have any of the regions within the lines. I don't have to worry about filling anything in. We've just got the nodes and then the lines, or the edges. We could decide to draw the graph in a different way. The lines do not need to be straight. They could be curved if you wanted to, just as long as the connections are the same between the nodes. And we could decide to place the nodes in a different location within my drawing. And again, just as long as the lines between the nodes remain and have the same relationship. So you might ask yourself, is there a better picture than the one that we've got? Well, we could rearrange things, and you might try to play around with this when I give you code for this. And change the locations for the nodes. And you only have to change it in the one spot here in order to still maintain the edges between them. The only issue you'd have to worry about that might become a little bit of a problem with, it might make it a little bit more difficult to read the graph, is if you place the nodes so that when you draw the edges, some of the edges might be crossing each other. So what I've got with the drawing here right now is that none of the edges are crossing, and so they call this a planar graph. And it's desirable because it's easier to read the information in my graph. I don't have to worry about getting confused about how the edges are connecting the nodes at all. And people can usually deal with maybe a couple crossings in the drawing of a graph and they're fine. So it's not like a big problem. But most people that are doing research that have anything to do with graphs like this, they usually prefer a drawing that doesn't have any edges crossing. So they would prefer to work with planar graphs if they can, when they go to visualize them. Now some of them might be very complex. You might have a large number of nodes, and then in that situation it becomes a very difficult issue to try to draw the graph without edges crossing. There are a number of different kind of algorithms to try to decide automatically, instead of hard coding inside the plot.java file where I've listed all the information here, but instead you write some code, and then given polynomial time, you could decide where to place your nodes algorithmically. Now it's shown that you can do this in linear time. I think that's about the best you can do with a graph that's planar, if it's possible to draw it without edges crossing, because there exist graphs that you cannot draw without edges crossing. So I could talk about that more later. I think it's a really interesting topic. Part of my work that I did during my PhD started to explore different surfaces, and then what are some of the issues with graphs that you could draw on those surfaces. And then again, the same kind of idea where can you draw them without the edges crossing? So it takes you into a deeper realm of complexity. All of the algorithms we've looked at so far this semester have to do with, and when we're talking about runtime, it has to do with complexity. So if you go into, and you're studying computer science and you take the third year class, I'm pretty sure it's Comp 382, where we've got computational languages. This gets into the finer details and the computational models that you could work with. So it's really good if you know graph theory to at least to the level that I'm showing you, because when you get into that class, you'll very much begin at the start of the semester taking a look at figures like this, but you've got directions on the edges, and you use them as computational models. So you're doing theoretical computing. And depending on the kind of model that you've got, there's certain kinds of difficult problems that you can solve. And so in that kind of course, they go into about 3 different categories, and throughout the semester, they take you from the first simplest model of computation to one of the most complex models of computation, the Turing machines, that represent the general purpose computers that we program with today. So someone had to do research in mathematics for that. It was Alan Turing. And he laid down the theory to demonstrate that if we've got this computational model, well, there's only a certain class of kinds of problems that we could solve in general. And that gets into the research of any kind of science that you could be interested in wanting to do research in. Is it a problem that's really difficult? Well, if a computer cannot solve that problem, then you probably don't want to do research in it either. So not only is this concept of complexity that you've been looking at and considering with the runtime for all these data structures that we looked at this semester, not only is it useful for programming, but when you really get into the more interesting stuff, you really look at being able to know whether you can even write a program to try to solve a problem. And that's a really good thing to know, because if you go get a job as a developer, the last thing you want to be in a situation with is your boss telling you to program something that's not even possible to write a program to solve. So it's a very foundational topic, and it's part of the reason why it's a required course in a computer science major. Not only is it like, it involves a little bit more math, and it's really good to know the graph stuff, but it's also good to know Math 225. So if you look back to your discrete math, your Math 125, then it really is a good idea to consider taking 225, because it gives you a really strong foundation to go into computational models. Very useful theoretical topics. If you can get into those and you really take them seriously, you can go off and you can become an excellent programmer. I think the very last thing we would take a look at is just one more method that I added to my graph data structure, so that I could just double check when we pass in the points for the edges I would like to draw. Are they actually a part of the graph data structure? Because otherwise there's no point in creating the arrays inside my client code, creating my graph up above, and then making my connections, and then setting up. You notice if I already have these arrays with the data like I want it, why am I then passing it in to set data for my graph instance? And it's because I just want to double check those connections that I've got, make sure everything's set up correctly. I'm programmatically taking care of the checking that I need to do, rather than trying to do it by looking at the output. So it's almost like a little bit of test code, although not getting too heavily into the test. And then I grab it again. We get the node data, get the edge data, what's going on there. This is code that I'm not expecting anybody down here further to get into with set data. I don't need you to get into this and try to understand all the calculations that I've got here. It's just a little bit nasty, because there really isn't any simple way to set up parallel arrays for the node information and the edge information without having to then get it ready to be passed in so that I can visualize it the way I would like. So there's a few calculations looking at getting the first like the x value and then the y value. And then with the edges, I have two nodes, so then you have to think about the first coordinate point and the second coordinate point. So I mean, it's kind of, I'm repeating the same kind of calculation over and over again, but you don't need to understand what's going on there. I'm not expecting anybody to program the visualization of the graphs. But if you're interested in it, I've got it for you here. And you can always play around with this, and you can try to simplify the code. If you can think of a way to do that, I'd be really curious to see what you might try. And I think a challenge like that is always a good thing if you're really A+, and you really want to get into everything and you've got the time for it. Otherwise, I know people are really busy at the end of the semester. Okay, I think that's about all I have to say. We'll be sticking with the locations for the nodes and sticking with this graph the way it is this week and next week. And when we get together for activity tomorrow, then we'll do a very similar kind of algorithm to what we demonstrated with breadth first search. We'll take a look at programming depth first search. All right, just to give you a quick look at node.data, we've got the first coordinate and then the label, and then if I want some extra information, this is the number that's inside the node, and then if I want to, I can give it another variable name, and we can have that printed beside each node if we would like. I'd probably update this as well, so we've got label. Maybe I'd add one more thing there. Value. Okay. And then edge data has x1, y1, and x2, y2, and then the rest is pretty much the same. All right. I hope you're enjoying getting into something I think is a little bit more fun and without needing it to be really that much more complex. And in fact, simpler than what we were looking at with binary search trees and AVL trees and then hash maps. So I really like it just because it's more visual and we get to draw it.